Welcome to our YouTube channel. Students, as you know that we are studying about the integral transform, in which we have completed our first unit, which is based on beta and gamma function. We have seen the definition of beta and gamma function. After that, we have seen some basic properties of that beta and gamma function. After that, we have learned about some transformation of beta and gamma function, and we have applied to different examples based on beta and gamma function. Now, from previous lecture, we have studied about the Laplace transform, in which we have studied the definition of Laplace transform and some other definition like pointwise continuity, then function of exponential order, then class A equations, and many more we have seen. Now we are studying about the Laplace transform of basic Laplace transform of basic function, Laplace transform of basic function. And we have seen that Laplace transform of 1 is equals to 1 upon s, while Laplace transform of e raised to at is equal, e raised to n, and which is equals to n factorial e raised to n plus 1, and then Laplace transform of e raised to at, which is equals to 1 upon s minus a, and we have already seen the Laplace transform of these basic functions. Now we are going to find the Laplace transform of trigonometric functions sine and cosine. So to find Laplace transform of sine 80 and cos sine 80 and cos 80. Friends, we know that sine 80, to find Laplace transform of sine 80, correct? Since we know that sine 80 can be written as e raised to I 80 minus e raised to minus I 80 upon 2i. We know that the sine 80 can be written in the form of e raised to I 80 minus e raised to minus I 80 upon 2i. So we can apply Laplace transform definition, that is Laplace transform of sine 80 is equal to integration from 0 to infinity e raised to minus st sine 80 dt, correct? And we can write it as e raised to minus st e raised to I 80 minus e raised to minus I 80 to I dt, correct? Now we have integration from 0 to infinity e raised to minus st into e raised to I 80 minus e raised to minus I 80 upon 2i. So we can simplify this e raised to minus st into e raised to I 80 minus e raised to minus st into e raised to minus I 80 upon 2i. We have e raised to minus st into e raised to I 80 minus e raised to minus st into e raised to minus I 80 upon 2i. Since y is constant, so we can take it outside from the integral, and we can write 1 upon 2i integration from 0 to infinity e raised to minus, taking minus outside, s minus I A T dt and minus as it is integration from 0 to infinity e raised to minus taking out s plus I t dt. We have just distribute integration to both integrands. As we know that integration is algebraic over two functions having addition between them. So 1 upon 2i is 1 upon 2i into integration from 0 to infinity e raised to minus s minus I a t dt minus integration from 0 to infinity e raised to minus s plus I a t dt. And if we want to integrate this, we will get 1 upon 2i as it is e raised to minus s minus I t upon minus s minus I a, and limits are running from 0 to infinity. Similarly, we can write this also e raised to minus s plus I t and minus s plus I a 0 to infinity. Correct? Now since in denominator minus s I a and minus s plus I a both are free from t, so we can take outside from this limit. So we can write 1 upon 2i taking minus outside and putting limits over t. If we put here infinity, we will get e raised to minus infinity, which becomes 0, and if we put t is equals to 0, then we get e raised to 0, which becomes 1. Correct? Similarly, if we take minus outside, it becomes plus 1 upon s plus I a. Similarly, if we put infinity, we will get 0, and when we put 0, then we will get 1. So we will have 1 upon 2i minus minus taking plus 1 upon s minus I, and this minus and this plus becomes minus 1 upon s plus I. Now we will try to simplify this, and we will get 1 upon 2i s plus IA minus s minus IA cross multiplication, and we will get s minus IA and s plus IA. So again, if we simplify this, we will get s plus IA minus s plus IA, s square minus IA bracket square. Since a minus b into a plus b will give us a square minus b square. So we will get 1 upon 2i plus and minus a get s get cancelled. IA becomes 2ia s square I square a square. 2 get cancelled, I get cancelled. We will get a s square I square means minus 1, minus and minus becomes plus a square. Since I square is equal to minus 1. Correct? So whenever we take Laplace transform of sin AD, we will get Laplace transform of sin AT, we will get A upon s square plus a square, and it is the form for Laplace transform of sin AT. Now, what we have done here, we are going to find Laplace transform of sin AT, and which is integration from 0 to infinity e raised to minus st sin AT, and sin AT can be written in the exponential form as e raised to iat minus e raised to minus iat upon 2i, and after multiplying e raised to minus st to this expression, we will get e raised to minus s minus iat minus integration from 0 to infinity e raised to minus s plus ia dt, correct? And after integrating and simplifying, you will get a upon s square plus a square. And one more easy method to find the integration or the Laplace transform of sin AT is as follows. Let's see that Laplace transform of sin AT means Laplace transform of e raised to iat minus e raised to minus iat upon 2i, correct? And as 2i is a constant, we can take outside from Laplace transform. So integration from iat minus Laplace transform of minus iat, and if we simplify this, we will get 2i. Since we know that Laplace transform of e raised to at, we will use as s minus a. By using this, we will find 1 upon s minus ia minus 1 upon s minus minus ia, and which is Laplace transform of e raised to at is 1 upon s minus. Now 1 upon 2i will give us 1 upon s minus ia minus 1 will plus ia. So after simplifying, we will get s plus ia minus s plus ia, cross multiplication, s square plus a square. We know that I is imaginary number, and it is square of that becomes minus 1, and this minus will cancel with that minus, and we will get s square plus a square. As minus is cancelled, we will get 1 upon 2i is equal to 2ia s square plus a square. 2i will cancel, we will get a upon s square plus a square, and it is the required result for Laplace transform of sin AT. In next lecture, we will try to solve one more transformation of cos AT. Till then, we stop at this point. Remember, we have done 4 basic results: Laplace transform of 1, that is 1 upon s; Laplace transform of t raised to n, that is n factorial upon s raised to n plus 1; and Laplace transform of e raised to at, which is equals to 1 upon s minus a. Then Laplace transform of sin AT, which is equals to a upon s square plus a square. In next lecture, we will try to solve or find the Laplace transform of cos AT. Till then, thank you. Bye.